Good morning, good evening from wherever you are, and warm greetings from a tremendously sunny and warm Edinburgh in Scotland today. So it is my absolute pleasure and honor to introduce to you my dear friend and colleague, Rick Chalaturnyk, who is a professor for geotechnical engineering at the Department of Civil and Environmental Engineering at the University of Alberta, and he also holds the NSERC Energy Simulation Industrial Research Chair in Reservoir Geomechanics at this department. Before Rick joined the university in 1997, he was a really successful entrepreneur. He co-founded a company on work in reservoir surveillance and was also the executive VP for another company working in the same area. And that entrepreneurial spirit has really translated into Rick's research, where he set up 4 absolutely fantastic. I had the pleasure to visit these facilities, geo-innovation laboratory environments that focus on large-scale centrifugal experiments, geomechanical experiments, 3D printing, and reservoir modeling technology. So if you ever have the chance to visit his labs at University of Alberta, you're in for a really, really great treat in terms of innovative science, innovative research, and laboratory experiments. These days, we are really concerned about energy transition. Carbon capture and storage is a key role in our bid to move towards a more carbon-friendly net zero society. And Rick has been a true champion of this field. He's been one of the pioneers. He's worked on carbon capture and storage for over 20 years, the International Energy Authority and the Weyburn Mid-Dale CO2 storage project. He's a member of the Aquistor Research Steering Committee, as well as many other CCS initiatives. And last but not least, I think Rick is a true Edmonton, or born and bred Edmonton person. He holds his bachelor's, master's, and his PhD degree all from the University of Alberta in Edmonton, all in geotechnical engineering. Without any further ado, Rick, I see you have relocated somewhere very nice in Canada. The floor is all yours for your presentation.
Great, thanks for that, Sebastian. I appreciate that. Thank you. And just for that purpose, that was Lake Louise. So those of you who have visited Canada for sure. So just to, I guess in the standard Zoom world, let me just resume this stuff. So do you see which slides do you see at the moment?
You see your PowerPoint presentation, but not in presentation mode, just the slides themselves.
Okay. Yeah. Let me switch the mode here. Hang on a second.
No, we're in business. Excellent.
Is it the full display now?
Yes, that's the wrong one. Now we see the preview. The previous one was.
Okay, good. Then let me just switch. That was it has to do with all this multiple screens. So that's good now?
That's perfect.
Okay, fantastic. Okay, well, thanks for that introduction. Yes, the background was Lake Louise, and it's also a sunny day in Edmonton. Might actually even get to 30 degrees C, so it'll be quite a treat. So thank you very much to the InterPore organizing committee for the invitation to speak today. And so I'll just, since we're a couple of minutes behind, I'll just dive right into it. Sort of the outline for the talk, I think one particular slide to provide some context around deformation and flow, just maybe to set the stage for the conversation. And I want to spend most of the time on this discussion of the journey, what has taken us down this path of worrying about geomechanical processes and its impact on flow, and really some of the really exciting work that over the last couple of years has been reported by Amir Hagee, Dr. Hagee, who had a poster earlier this week, and then finish up a little bit with a discussion on CCUS, where we're applying this, and some discussion around next challenges, maybe what I think is the one particular challenge I think that's important for us to look at. So a fantastic diagram. If many of you have not read Heffer's article 2002 early on, and spent a lot of time worrying about stress change and flow and things, and had conceptually developed a map like this. And it's important. This one is actually a particularly important plot from the point of view of speaking about this issue of flow and geomechanics, because you know, if you look at this particular plot, you know, if you're a geomechanics person, you're thinking stress strain and everything else, and so you plot shear stress versus strain, and you get these stress strain curves, and they change if you change confining stresses and so on. But when it comes to flow, it's really the bottom part of this curve which tends to be the most important. And so what you're looking at is how volume changes occur in the samples. And you either, as the sample is shearing, you get contraction, or depending on the confining stresses and density and a bunch of other things, you can have volume increases, and they generally will refer to that as dilation. But in this map of permeability in this space of shear stress versus mean stress, you can see some of the words that we talk about in terms of permeability or deformation processes that would impact multiphase flow. So if I have a particular behavior over here, which is dilational, brittle failure, microcrack development, and so on, I can have this issue about permeability decreasing, increasing, what is happening. But if I'm on the right-hand side, I can have a region which, from a geomechanics point of view, I'll look at as elastic. But if I start to yield it, you know, in hydrostatic compression, I'm going to collapse the pores. And then I'm going to lead to sort of different changes and decreases in permeability. And this becomes a very complex space to deal with. You know, if you look at most of the testing, you know, I will say that in looking at some of the presentations over the last bit of here of InterPore, absolutely humbling to look at the amazing kind of work that's being done, and the details, all the way from digital rock physics all the way through to larger scale problems and multi-scale problems. But in general, most applications, when they look at changes in permeability, will look at it relative to this red line. They will look at it where I'm sitting in here, and there's very little shear stress happening. And so that's the part that has been sort of dominating a bit of our conversation in the early 2000s, when we started to look at issues like steam-assisted gravity drainage and applying these sequentially coupled techniques to it. And for those who haven't looked at SAGD, it's a pair of horizontal wells drilled, and you inject steam in one well, and it loses its heat to the bitumen, the very viscous bitumen, and the bitumen flows under gravity to a lower production well. But what happens is that because of pore pressure change and because of temperature change, it results in a very complex stress field that develops, where between steam chambers, I get changes in horizontal stress, I get changes in vertical stress, it generates shear stress. And one of the things we noticed, especially from this early underground test facility project, was that if I plot a sort of normalized plot of temperature, so this line, this vertical line here, is like I'm riding on the edge of the steam chamber as it's developing, and I plot how the temperature change is going out. It normalizes quite amazingly, actually. And so what you get is this region of 5 to 10, maybe 12 meters out, where the temperature penetrates. But then beyond that, you're at this much lower temperature, and you're in a zone that's undrained. There's really no temperature change out there. But when you look at the right-hand plot, what you see is that the pore pressure migrates out substantially larger distances. It can go out 20 to 25 meters. And so there is this change in permeability that is occurring because of this change in geomechanical processes. And we needed to try and understand that. And typically what happened was, I thought I would just show in this picture, these were the days when you could, you know, you go to an outcrop and you fire up the chainsaw and you get a block sample to do some testing. And this is actually very dense McMurray Formation sand that doesn't have any bitumen in it. And so you can collect samples and do some testing. And we had done a bunch of that. And you know, there were all the way back to the late 90s, had a lot to do with mining and mine stability, but a lot of stuff looking at thermal flow and behavior under low confining stresses. And what you found is, you remember in the geomechanical response, we talked about volumetric strain, is that we tended to always plot these relationships where you'd have volumetric strain and porosity, which you can do, lots of forms of them. There's just a couple of them here. There would be some relationship, a cubic relationship, where you could embed volumetric strain. But what we didn't do back then was there wasn't a recognition that under isotropic stress, you would get volumetric strain, and under shear stress, you would get volumetric strain, but there was no differentiation between the two of them. They would just apply to volumetric strain. And so what was interesting is that we started to think about, well, okay, but there's some things that are happening here. There's a difference in the way that the pore geometry changes under isotropic, and testing has been going on in that area since I'm the historian, but a long time. But the other issues now, but shear induced now changes the pore volume geometry, changes the way the grain shapes are, changes tortuosity, it changes all those sorts of things. And so there were early tests where there were effective perm to water tests that were done. Bitumen was immobile. You did it at a low temperature, so the oil phase was immobile, so you could measure the effective perm to water. You had this geomechanical response you see in the circles here, range of stress pass. And if you look at this particular plot during a sort of stress strain curve, if you want to call it that, you can see that you went through 2-3 orders of magnitude in effective perm to water. And so based on a bit of this work by in late 2000s, 2009, a fellow did a really nice master's thesis at the University of Texas at Austin, and followed up from a bunch of this kind of work, and sort of looked at this sort of effective perm to water change. Again, this is another series of tests, different stress path, to look at the impact. And you can see here 1, 2, 3 orders of magnitude due to volume change. And so what happened is in late, sort of early 2010, young fellow Sam finished a master's. He was kind of motivated by the work by Kahn, and said, well, I wonder what the impact is from a simulation point of view. So he took this early work. There were some issues geomechanically with the data, density and dilational characteristics and stuff, but took the data, developed these relationships where he had residual oil saturations, irreducible water saturations, endpoint stuff, developed a sort of Corey functions as related to stress, sort of compaction and dilation, and put this into a model and ran some simulations around a sort of conventional depletion characteristic, built a 400, sort of essentially 400 by 400 meter model, producer in one, quarter spot pattern, producer, injector, ran some sequentially coupled simulations with depletion characteristics. But what was interesting is that when he put in these relationships about how relative permeability would change or capillary pressures would change endpoints, had quite significant shifts. These are an example of a 13 MPa injection pressure water flood, 16.7 MPa injection water flood. You had geomechanics happening in the model where under certain conditions you would have compaction dominated and dilation. Other cases you would have dominated by a higher injection pressure, and it would be dominated by dilation. And you had these quite significant shifts. Well, so the question was, these are quite substantial, change breakthrough times and everything. So how much was permeability impacted by these geomechanical processes? So there were a few things to confirm. And so we returned to the lab and to start thinking a little bit more about specific sort of higher quality tests around the relative permeability, what would happen. And Mohammed Hamoud did some really nice work, 2010, 2012. And what we did was we have a procedure where we could reconstitute extremely dense, relatively dense, in the words of geotechnical engineering, very high density, 250% relative densities. So you could get, you recall the stress strain curves. You would stress this material, and you would get dilational responses in the sand. And what you would see is that if you looked at the red dots, you would get a reduction in absolute permeability in the early parts of the curve. And then as the sample dilated, which is this blue curve, which is the increase in porosity, then you would get an increase in permeability. And so the idea was, well, okay, what did relative permeability look like? And this was the start of the journey in some ways, in my mind anyway, for us. So because what you see are the initial relative permeability curve, steady state, and the curves on the right will show you the position in the stress strain curve. So you run the tests, you determine the relative permeability curves, and then you shear it, contracts a little, shear stress rises, and you can see that the curve shifts. And then if you keep going, it shifts some more. But as soon as you pass peak, as soon as you fail the sample, still dilating, interestingly enough, the relative permeability curves contract. And so if I continue, then there's only a modest change. And so this was really an interesting thing in how geomechanical response is impacted. But the one that was actually probably more dramatic, I think, which I think in some ways up until probably the last few years, where people have been doing some really amazing pore scale work, including Amir's work, which I'll show in a second, is that he had repeatable tests on how these irreducible water saturations shifted and how SORs shifted, just because of geomechanics. And so if you see on the left hand side, volumetric strain on the left axis, axial strain on the bottom, and these sort of sets of points here is this volumetric strain curve. You can see that you get these changes in residual oil saturations happening where you get this shift from contraction to dilatant behavior. And it's also noted here in the SIR shifts. So this was really quite interesting. And so the question was, well, what fundamentally is causing the shifts? Is it real? Is it repeatable experimentally? And so much like many people, and there's definitely a significant amount of sophistication in this particular area, but and definitely some work in the last couple of years that have really dramatically pushed this forward. We said, well, could we use the kind of work we're doing geomechanically in particle models, discrete element models, and in this particular case, PFC 3D. We wanted to do this in 3 dimensions. And so, you know, we developed a PFC 3D model. We could deform it, then repeat essentially what would be X-ray CT, but we would extract the pore geometries from there, and then we would build an equivalent pore network model. And we were gracious to be given the ability to use the pore flow model from Imperial College, Dr. Blunt and colleagues. And, you know, initially sort of were able to go through and match absolute permeabilities and so on. And then move forward to trying to look at, okay, where are some, you know, where are some of these things really making an impact? So you had changes in rel permeability curves that you could get from the pore networks. And the simulation that you see is, I threw this on here because it really gives you a good sense of under shear stress, how these pore geometries are changing. And under even small amounts, you get quite significant changes in pore throat geometries, pore network topology. And so looking at things, you know, trying to, in our lab, trying to look at how these idealized 3D printed rocks could be used to really start analyzing this in detail. What was also a shift for us was the start of this particular work. Dr. Juanes and colleagues, Dr. Zhao, and released this work in 2016 that really did some fantastic work on shifts in water wet to sort of oil wet to capillary numbers. And it was really a fascinating study. I think it spurred on a lot of work. There were studies done to try and match this data. But what was, from a reservoir geomechanics point of view, the question we asked ourselves was, well, what would happen if this pore network started to change during injection? So if effective stresses were changing, what would happen? And so it was interesting in their study that when they looked at numerically what would happen if I changed the spacing between these posts, you can see what happens if I have close, excuse me, the close spacing and I moved to wider spacing into the blue, the lambda value going from 1 to 4. And you can see quite a shift in the way that the filling processes occurs, the way the contact angle shows. And this was this kind of initial thing that started to look at in terms of its impact on wettability. And so this was actually interesting, an indirect measure of geomechanics in a way. The other part that for us was interesting was in certain parts of this process is stress path. And stress path, so if I go in, stress path has to do with which direction I'm going in this sort of shear stress, mean stress plot, the Kess-Heffer's plot that I showed you before that had the nice colors in it. You know, here again is the yield point or critical state line, he called it. But depending on how I move in this space, do I move in this direction, which is sort of what's referred to as triaxial compression, or what happens if I move to the left? And so there are a lot of processes that we involve ourselves with, like the water floods, where I go under injection. And so what I do is I move to the left. I move in this sort of A path. I start at some position, some effective stress position, but then I move to the left. So the question is, if I'm moving to the left, does it make a change in my permeability characteristics? Does it change the way I need to be thinking about how these permeability variations are occurring? And so went into the lab, utilizing that same technique to create these high quality samples, and did essentially what you would think of as pore pressure injection tests under isotropic stress conditions and under anisotropic conditions initially. And so in this plot, I have volumetric strain. So it's that measure of pore volume change, pore geometry, sort of tortuosity kind of change, versus in this particular case, it's plotted versus horizontal effective stress, because these were all done at a ratio where the horizontal stress is lower than the vertical stress. So it's the one that drops the fastest. And so what we do is we establish an initial stress state, start pore pressure injection. And when you do that, this effective stress drops. And so if you're in isotropic conditions, you basically move up and down this compression curve that I think most people in the InterPore community would recognize. But if I have an initial anisotropic stress state and all I'm doing is injecting pore pressure, I reach a critical point here, depending on a lot of factors, but I reach a critical point when in actual fact, I get very rapid and very large changes in pore volume because of the shear dilation that is occurring only under pore pressure injection. And so this is not a geomechanics lecture. We're wanting to sort of get at this issue of flow. And so if you look at this plot, it's kind of plotted in a slightly different way, but in this particular case, the bitumen phase was held immobile. And so I'm plotting the effective permeability to water versus porosity, so a proxy for volumetric strain. Here's this curve again on the left-hand side, the volumetric strain versus horizontal stress. Here's where I start. And if you look at this, I've got a point here where I start down here at this A primed point. This is the start of the curve. And I'm measuring it as I go through this procedure. Basically what happens is I get an increase. And when I unload, I return to this point and I basically get effectively no change in the effective permeability of water. There's no change in the pore geometry. There's no change. In this particular case, a very dense sample, so I get very little hysteresis. I'm not getting a lot of compaction-induced movement, but very little change in effective permeability. But if my initial stress state is anisotropic and I increase the pore pressure, what happens is I load, I go all the way up and I get these large volumetric strains, and I unload, I get all this plastic deformation. And basically what happens is I go from 10 microdarcies to 6,000 microdarcies, substantial change. So this again really started to show this sensitivity to stress change in terms of how these permeabilities change. And as we started to tackle much larger problems, and this is something again in the InterPore community, a lot of people are worrying and doing some amazing work in this area, multiscale modeling, sort of started to move all the way from the pore scale all the way to the full reservoir scale. In our particular case, our focus was primarily on trying to handle the geomechanics. But again, you know, our world is almost entirely this sort of sequentially coupled or coupled reservoir geomechanics. So we're trying to figure out this relationship between flow and deformation. And so, you know, this is Bo did some fantastic work in this upscaling workflow where he could, you know, he could take very multi-million cell, you know, and drop them by orders of magnitude in the size and recreate, in fact, the same behavior. But, you know, the challenge became, again, this is a conversation about flow. The challenge became about flow. What do you do? So we, you know, we had techniques to upscale these heterogeneous blocks. This is a plot of deviatoric stress versus axial strain, upscaling in these blocks and trying to look at how now you have different behavior if you load in the X, the Y, and the Z, and it changes the sort of geomechanics behavior, if you like it, into different cohesions and different friction angles, different modes of failure. But the trick was it also changed permeability in a substantial way for upscaling. So what happened is, if you look here in this particular, this takes this one block, this one scenario of upscaling, looks at this behavior and says, okay, if I look at this normalized permeability, sorry, the green line is the deviatoric stress. So think of the green line as stress strain curve. I get a blue curve that matches the vertical effective permeability and a red line that matches the horizontal permeability. And these all changed based on how this mode of failure occurred. And so you would have flow paths developing under shear failure and everything. So it was really quite dynamic and presents actually quite a challenge when you're thinking about this, trying to match both the flow response and the geomechanics. And I think probably this is the part that answered a lot of our questions, was Amir's PhD work, 2018, 2019, and so on. Really, Amir did some fantastic work, and I think there were lots of simulation work this time, but he really took a hard look at how to do this experimentally, and I think answer some of our questions around this increase in irreducible wetting phase saturations, and so on. So just to share with you some of this work that he did, you know, the premise for this was that you come in here and you could do the normal sort of characteristics in terms of a capillary pressure curve. You could calculate that. But as you actually depleted a reservoir, effective stresses would increase, pore sizes would decrease, and then you could actually repeat this exercise. But what would happen is that you would trap certain fluids in the pore spaces, and it would change the capillary pressure curves. And so you would change them. You would change SW, irreducible water saturations, and so on. And so this had an impact on behavior. And so this was his hypothesis. I took a look at this work. Had to do it the old-fashioned way. I guess I call it the old-fashioned way these days because, you know, these days you need an X-ray or a CT scan machines to do all this stuff work. But he put together a system that allowed him to do nitrogen brine tests on these core samples, micro CT work to look at some of the pore spaces. And what he discovered was that when you look at in the upper right hand, you'd see the same porosity reduction, permeability reductions with the increase in effective confining stress, which is, you know, pretty much the expectations. But what he found was the relative permeability curves would shift as a function of this mean effective stress. And so you had increasing effective isotropic stresses, changing these relative permeability curves, and in particular, the capillary pressure curves would change as well. So that was in Berea sandstone. And so also took on looking at limestone as a different porous medium, looked at how these changed, did some work in trying to look at how pore throats would change in this work. Capillary numbers would change with effective stresses, quite substantial. This was an interesting part where he took on looking at a fractured sample. And this is kind of really has changed a bit of our work now in how people want to look at fracture flow. This also led to changes in the relative permeability curves along the fractures, with changes in effective stress, which you'll notice that this stress shifted the curves in the opposite direction to porous medium, and you get really quite substantial changes with capillary pressure. We started to sort of better, for us to better appreciate how irreducible water saturations and other variables would change as a function of effective stress. And one of the nice things, I think, is that we've had some great collaborations with Sebastian and more recently with Dr. Blunt, really providing some great insights about how to actually think about this in a much more fundamental way. And Amir's done some great work given some of that feedback and advice from Dr. Blunt and Dr. Geiger, and it's sort of adjusted the pore flow modeling technique with a stress term in here, so he can actually shift this to match curves. And maybe just in the final components here, just to give you a sense of where this has an impact and where we're applying it now, is that in the CCUS field, a lot of people doing a lot of work around residual gas trapping and other things, and pore space modifications, and we're facing some of the same challenges in Aquistore. It's quite deep, 3,300 meters. If many people haven't heard about it, high temperature, 115 degrees C in situ, very, very saline, 320, 330 grams per liter. Lots of field data, lots of observational data, lots of history matching has been done. Dr. Alireza Rangashakri in our group is just doing some fantastic work. But what you notice in the bottom here is that what we're finding is that as you cool in the reservoir, the injectivity can go up by orders of magnitude. You can history match the data. It has definitely a relationship to minimum effective stress. There are certain things happening here, potentially thermal induced fracturing and other stuff. But the part that is intriguing is that we're using sort of non-Aquistore specific relative permeability curves. And so history matching, I'm going to history match to the seismic data. And so what we're going to do is utilize some of Amir's technique, go in and look at this. He's applied some of his sort of sigma PFM techniques to look at rebuilding what the capillary pressure curves under imbibition and drainage conditions might look like, what the relative permeability curves like. And then we're going to conduct some experiments in the lab using the same technique. So as a next challenge, kind of to the InterPore community, which I think is important, is this issue of shear. Under all of these cases, under small amounts, large amounts, depending on the characteristics of the reservoir, generally are almost always anisotropic stresses. So even under pore pressure injection, you're going to induce shear. So how much of all of these extremely complex flow relationships that are being looked at, wettability changes, people are starting to look at how deformation can change the characteristics of wettability or the interpretation of wettability, and so on. So I think this is where some of the major challenges occur. So complex stress paths moving to not only just mean but shear stress changes, pore size and geometry changes, and then how those affect those flow properties. And so in our environment, Sebastian had referred to this a little bit, these geo-innovation environments, we're trying to utilize these as much as we can. Trying to look at this sort of the experimental facility, 3D printing and some other stuff, fracture flow, trying to look at fracture flow in a slightly different way using sort of an arrays of fiber optic sensors to look at how pore pressures will vary in fractures as they are sheared. So again, shear deformation. So maybe just let me conclude with a little tough. I tried to identify a lot of the people involved, but the pictures you see there are the absolutely amazing team that have been along with the journey in the Reservoir Geomechanics Research Group. Those are all of the brains and all of the very, very smart individuals that are contributing to a better understanding of these processes. So with that, thank you very much. I should conclude and look forward to answering any questions anybody might have.
Thank you much, Rick, for a really interesting, really enlightening talk. I think we're a little bit short for time, but we may have time for one or two questions from the audience. So if check, there's nothing coming through to the chat yet, but if someone wishes to ask a question here on Zoom, just raise your hand, please. Well, in this case, I'm going to ask a quick question for Ulrich. So the Pore-space modeling, which I also had a little bit of involvement in, I found it really fascinating because it helps us digital rock physics to understand some of the fundamental physics. What do you think in your mind is missing to bridge scales? Because we're looking at the millimeter, sub-millimeter scale, but what we want to do is have the right properties to put into your reservoir models at the meters, tens of meter scale. So how do we upscale geomechanics?
Yeah, I wish I had the answer. I think that's the clue. Again, I'm not a digital rock physics individual. I'm overwhelmed by the degree of work that individuals are doing, even in this InterPore conference. I know some individuals doing some fantastic modeling to determine the yield envelope. And upscale it to a 50 by 50 meter by 50. Well, even that's not even small, but a 50 by 50 meter grid block size. I don't know. I think that's where some of the big challenges occur at the moment. And I know it for sure from the point of view of geomechanics. I mean, when you're trying to look at the coupling, I mean, it's difficult enough as it is with just flow, but you throw some deformations in there, it becomes extremely difficult.
Well, it sounds like we have plenty of more research to look forward to coming out of your group and out of this InterPore community.
Yeah, some of these X-ray CT people have to figure out how to build the tiniest triaxial cell known to man and just stick it down inside the X-ray machine.
I see Tisa has his hand up.
Yeah, it's a very nice talk, and I have a question, general question related to this ideas you presented here. I'm sort of involved a little bit in the nuclear waste business. Yeah. So are there, because some of those environments have some pretty high temperatures, when you are dealing with, for example, underground waste repositories.
Right.
So are you aware of these theories? That's one question. Number two is that when you develop constitutive models for this type of phenomena, at least in the nuclear place, one of the issues is the people are questioning the constitutive models, how good they are.
Right. Yes. Well, I think in the nuclear world, and I haven't shown it a lot today, but there's a lot of people working. It has to do with fracture flow. People are worrying about excavation damage zone, development of fracture networks around these zones, and how flow is going to be influenced when heating occurs. And I think if you can imagine into the kind of mechanisms I reflected on, if there are going to be deformations or something occurring in there that are going to shift your capillary pressure relationships, or are going to shift your relative permeability relationships in terms of two-phase flow around those excavation damage zones, and your modeling is not capturing it, then you actually don't know where you're at. And I guess that's the kind of the challenge to the community, is that in all of these systems, deformations are occurring. And the question in some ways is we need to answer ourselves, is this a first order effect, or is it a third order effect and you can just forget about it? Like the actual flow physics component is so dominant that, yeah, a little deformation, yeah, it doesn't impact it. But some of the cases that Amir has run, for instance, with just putting some of his relationships, and that didn't even involve shear. He can shift recovery estimates in a reservoir by 50%. Well, those are substantial numbers. And so, you really, there's a lot of work that needs to be done to determine, the degree of relevance for that stuff. Absolutely.
The main issue is that reason I asked this question is that in the nuclear business, these models had to be simulating for the large periods. We are looking at million years. So that if you do any mistakes in this type of analysis, that may have a major effect on actually your safety requirements. So I'm glad at least people are thinking about these issues.
Yeah, good. Yeah, good. Thanks. Yeah.
Okay. Thank you, Tissa, for the question. Thank you again, Rick, for another great talk. Thank you to the audience for joining us for this invited lecture. I certainly do hope I see you in Canada at Lake Louise in not too long of a time.
Sounds good. Sounds good. Thanks, Sebastian.
Thank you.